the solution to the vortex panel method depends on how we have clustered our nodes, or how we've placed those nodes along the surface of the airfoil. So if you've downloaded an airfoil and were given, if you were given an airfoil, usually you'll have that airfoil defined as a bunch of points that you can just read into your code. And you could use those points as the corner points of the panels, and just connect each of those. Or you could fit a spline and then do some kind of a clustering, like we'll show here in just a minute, where you cluster more nodes at the leading or the trailing edge. That takes a little bit of work, but that can be done. The challenge with this is that you don't know exactly where the leading edge is in general if you just have a set of data points that define this airfoil. So in general, it's easier to control the clustering if you have a definition for the airfoil in terms of an equation. It's nicer to be given an equation for the camber line as a function of x and the thickness as a function of x, which is the case for example, the NACA 4-digit series that we've talked about before when we talked about airfoil geometry. But if that's what you're given, then at any x location, you can get an upper and a lower surface coordinate. And anyway, so we can cluster in x and or have really nice spacing that we've defined in x, and at any x location we can compute our upper or lower surface. So why do we want to cluster? Let's look at an airfoil here, and let's just plot a notional pressure distribution over this airfoil. So most airfoils have something that looks like this for a pressure distribution, and actually usually pressure is plotted upside down. So this peak here would be a very negative pressure. It's just convention. We flip the y-axis when we plot pressure. So anyway, a lot of pressure profiles look something like this, where we have a rapid decrease in pressure right here, right at the leading edge, and then we increase in pressure slowly, and then at the trailing edge, it drops off rapidly again. So what this tells us is in the forward part of this airfoil and in the aft portion of this airfoil, the velocity and the pressure are rapidly changing in those regions. And any place where we have properties that are rapidly changing, we generally want to have a finer mesh there, or a finer grid, so that we can capture those gradients to higher resolution. And as we see here in the center region of this airfoil, the velocity is changing, but the gradient isn't nearly as high for pressure and velocity as it is at the leading and trailing edges. So the most common method for clustering nodes on an airfoil is called cosine clustering. So let's draw what that kind of looks like on this airfoil. What we do is we go to the center of the airfoil and we basically draw a circle around that airfoil. And instead of dividing up the x locations evenly, what we do is we divide this circle up in even increments of some delta theta. And that delta theta depends on how many nodes we want on the airfoil. And then the x location, the way that we divide up x is that we then take the x coordinate of each of those points with a delta theta, and that becomes the x coordinates of interest. And what happens here is that along the x-axis, what that's going to do is it will provide closer x coordinates near the leading and trailing edges. So as you move here to the leading edge, our points will get closer, so that the delta x spacing here at the leading and the trailing edges are much smaller than the spacing near the center of the airfoil. So this is called cosine clustering. So let's develop an algorithm here for cosine clustering. Our algorithm is going to be a little bit different depending on if we have an even number or an odd number of nodes that we want on the surface. If we have an even number, then at the leading edge, if this is my leading edge and this is my camber line coming off of the leading edge there, if we have an even number of nodes, then we'll have a panel that actually spans across the leading edge, but we won't have a control point or a corner point of our panel that falls on the camber line. If we have odd number of nodes on our airfoil, then there right at the leading edge, we will actually have the corner of one of the panels, and we'll have panels that come off something like this, okay? So that's the difference here. Now, I've heard that an even number of spacing gives better results. I haven't studied it enough to know that, but we can write an algorithm depending on if you want an even number of nodes or odd. So let's start with odd. If we have an odd number of nodes, then we would compute first a delta theta that depends on the number of nodes. We would take pi and divide it into the number of nodes over 2. And because n is an integer, we want that to be a real number. So we will take the real number of n, which is odd, divide by 2, and that's in the denominator there. We divide pi into that many sections. So then we would say for I equals 1 to n over 2, then our x over c, or percent chord, is equal to 0.5 times 1 minus cosine of I, which we need to be changed into a real number, it's an integer, times delta theta. And so that gives us our x over c component. So that will give us n over 2 points. And then the center point, we know, is at 0, 0. So we can say, the center point, if we're, I should say, we traditionally start on the lower surface of this airfoil. And so we would start here at the trailing edge and go in this direction. So and compute points as we move along here. Okay, and so we would go up to n over 2. So this is our n over 2 location, and then our center point, because we have an odd number of points, is just going to be at 0, 0. And then we keep walking in this direction back to the trailing edge using the same x locations as we did before, but now storing the upper surface as we move back to the trailing edge. Okay. Okay, if we have an even number, then delta theta is equal to pi over real of n over 2 minus 0.5. And then our algorithm would be for I equals 1 to n over 2. The percent chord, or x over c, is equal to 0.5 times 1 minus cosine of the real I is an integer, we need it to be real, times delta theta minus 0.5 delta theta. Okay, so this would be the algorithm then for finding all of these locations on the x-axis if it was even, and this is the algorithm if it's odd. And once we have all of those locations along the x-axis specified, then it's just a matter of walking along from the trailing edge to the leading edge. We'll usually walk along the lower surface first, and then back up along the upper surface, and simply store all of those points that correspond to those X locations that we've computed here. We'll store those in an array, and those now will become the corner points for our Vortex panels. Now, I have to say that there's something special about cosine clustering. I'm not exactly sure what it is, but cosine clustering tends to give, from my experience, the best the best solutions in terms of grid resolution. So as we're going to find that we're going to double the grid and make sure that as we double the grid and continue to double the grid or make our node count higher, that our lift or pitching moment approach some value. So if we looked at as a function of the number of nodes that we're using, we want our lift coefficient, for example, to level out. And at some point we're going to say, you know, this is level enough, and this number of nodes right here is sufficient to give me a good solution. And for some reason, cosine clustering just grid resolves more quickly than other clustering methods. And I think part of it has to do with the theory of conformal mapping, that airfoil aerodynamics is actually very closely related to dynamics of flow around a cylinder. And so in the conformal mapping section, we'll learn about that. But I think that's why cosine clustering works so well for the Vortex panel method. But you can experiment with different clustering methods and draw your own conclusion about what is best and how best to handle this.